All right, in this video, we're going to do an example problem from your notes on calculating atomic mass, which is the weighted average mass of all the isotopes of an element. But at the beginning, I just want to talk about what atomic mass, what this sentence actually means, and how it's different from what we've learned before with mass number. It's a really common misconception that these things are the same. So just to refresh, let's review a little bit about mass number, which we've talked about. The mass number is the number of protons and the number of neutrons in the nucleus of any atom or isotope. So it's literally a count of how many protons and how many neutrons. So when you have the mass number, it's always going to be a whole number because you can't have part of a proton or part of a neutron. You're literally just counting them up, and then you get a whole number, which is the mass number, and you can put that here. So what we can do, if we're talking about certain elements, like carbon as an example, carbon has a few different isotopes. And remember, isotopes just means that it has a different number of neutrons. Okay, so, forms of carbon, there's two naturally occurring stable forms of carbon. There's carbon 12 and carbon 13. So those numbers here written in isotope notation, the 12 and the 13, those are the mass numbers, okay? So carbon 12 has a mass number of 12 and carbon 13 has a mass number of 13. What we do on the periodic table, when you have all of these atomic masses here, they have to take into account every form of that element, okay? So like we're talking about carbon, there's not just one type of carbon, there's a lot of different types. So when we get its mass, we need to make sure that we take into account all the different forms of carbon when we're reporting a mass. Because if we scoop up some carbon, not all of it is going to have a mass number of 12. Some of it will have a mass number of 13. And so what chemists will do is we don't want to just take a regular average. We don't want to get the average of 12 and 13 and say, well, the mass is 12.5. Because we need to consider how much of the carbon is carbon 12 and how much of the carbon is carbon 13. So if we think about, these are rough numbers, but let's say about 99% of the carbon that you find is carbon 12 and about 1% is carbon 13. So the vast majority of carbon atoms that you would randomly pick up are going to be carbon 12. So that's why when you look at the atomic mass of carbon, it's much, much closer to 12 than it is to 13. Okay, because more of the carbon is carbon 12. So that is what we call a weighted average when we're taking into account the abundance of the isotopes. All right, so just like your grades in this class are weighted, 80% tests and quizzes and 20% homework, that's the same thing with an atomic mass, is the masses are weighted depending on how abundant they are. So there's a really easy formula to do this, just like how you could calculate your grade in different classes. This is the formula for calculating any weighted average. So you're going to take the percentage abundance of each part. So essentially these will all add up to 100%, or 1 if you're using the decimal form, which we will be doing. And then the in parentheses part is going to be each of the masses of the individual isotopes, in our case, since we're doing atomic mass. Okay, so this is the formula we're going to follow. We're going to work through this example from the notes so you can follow along. This is for magnesium. So it gives us this data, and it says that there are 3 isotopes of magnesium that we need to take into account. So magnesium 24 has an exact mass here of 23.99 AMU. So if they didn't give you these masses, you could actually just use the mass numbers. Notice they're very close. But since they're giving you these exact numbers here, you want to use these to get the most accurate answer. But just know that if they're not given, you can still do the problem using 24, 25, and 26. Okay? So magnesium 24 has a mass of 23.99 AMU, and the abundance is 78.70%. Magnesium 25, 24.99 AMU with an abundance of 10.13%, and magnesium 26 has a mass of 25.94 AMU, an abundance of 11.17%. So notice that these together are going to equal 100%. And then we also want to just consider, just to think about what answer we're going to get here, magnesium 24 if we look at the abundance, is 78.70%. So if you were to just guess what the answer is going to be, what is going to be the weighted average or the atomic mass of magnesium, what would be a good guess looking at these masses here? So hopefully you picked the first mass, 23.99 AMU. Hopefully our answer is going to be close to this number because it's the one that's going to have the most weight in our calculation. It's going to take up 78.70% of this weighted average that we calculate. Okay, so to set up our problem, I'm going to color code this to make it easier to see. We're going to be following this formula. Okay, so I'm going to take, and it doesn't matter if you do the mass first or the percentage first, but you just want to be organized here. So if I put, I'm going to just start with the 23.99 AMU, and then we want to multiply that by the abundance, but we want to turn this into the decimal form. We need to move decimal 2 spaces to the left. I'm including that 0 there for sig figs. We'll get to that later, but you want to include that. And then, oh, I wish I wrote that in black. I'm trying to color code this. All right, so then we want to add the next piece, magnesium 25. That has a mass of 24.99 AMU. And the abundance is 10.13. So again, I want to move this decimal. And then the last isotope, magnesium 26, its mass is 25.94 AMU. And 0.1117 is its abundance. So we're going to type this into the calculator. The way it's written, your calculator knows its order of operations. So you can type this in exactly as you see it, but you actually don't even need to use the parentheses. So why don't I try to show you how I'm typing this here. So we're going to do the 23.99, and we multiply that by the abundance. I'm going to hit times 0.7870, and then plus, your calculator will know what to do, 24.99 times 0.1013 plus 25.94 times this abundance, 0.1117. Okay, and then before I hit equals, remember we said we think the answer should be closest to this number. Out of the 3, it should be closest to the 23.99 because that has the highest percentage. I'll hit equals. And it is pretty close to that one, right? Because this is really close to 24. So ends up being pretty close to that. We're going to round to 2 decimal places. In short, we'll learn really why in our math unit, but these are all to 2 decimal places, so we want to put our answer to 2 decimal places. We'll use red here. So if we want to go to 2 decimal places, it's going to be 24.3, and then here, the 0, which is where we want to round, we have to look at the next number, and it's a 9. So 9 is greater than 5, so this needs to round up to a 1. Right, so it's going to be equal to 24.31, and then the units here are AMU, because these all had units of AMU. All right, so that is the atomic mass that we calculated for magnesium. And the nice thing about these problems, besides what we just did, that we realized it's pretty close to that number there, we can also check our answer in a different way. Right, so we just calculated the atomic mass for magnesium. Where might you be able to check your answer? Someplace that has the atomic mass of magnesium. Your periodic table has the atomic masses for every element, so you just need to find magnesium. There it is. and the mass is indeed 24.31. So it's actually exactly what we calculated. Sometimes it might not be the exact number, but it'll be very, very close. And this is a really nice way for you to verify your calculation, right? So that's just an example of one atomic mass problem, but you're going to follow the same form. Doesn't matter how many different isotopes there are. You can do this with 2 isotopes. You can do it with 4 isotopes. But you just want to follow this general formula where you do the mass times the abundance plus the mass times the abundance plus the mass times the abundance. And then use those checks to see if your answer makes sense. All right, good luck.